Hello and welcome back to another installment of NatLab video. In this video, we will take a look at a quick way to measure particle size using the dynamic light scattering principle. Particle sizing has a variety of applications in industry. Particle size can affect many properties including flow properties. Smaller particles tend to aerosolize better than larger ones, and smaller particles will tend to have higher suspension viscosity than larger ones in liquids. For example, particle size can determine the flavor of food products, reflectiveness and glossiness of paints, or the effectiveness of an inhaler. Particles experience Brownian motion when suspended in liquids. Random collisions with solvent molecules causes particles to diffuse throughout the liquid. Laser light is directed onto the particles and the light scatters. The observed intensity of the scattered light is a result of the interference of light scattered by each element, thus it will depend on the relative positions of the elements. After measuring the fluctuations in light intensity, an autocorrelation function analyzes the data. The normalized intensity autocorrelation function is dependent on the delay time tau, the intensity detected at time t, and the normalization factor. The diffusion constant, which is proportional to the lifetime of the exponential decay, can be found by fitting the correlation curve to an exponential function. From the diffusion constant, the particle's diameter can be found using the Stokes-Einstein equation. The parts of the equation are the diffusion coefficient, the Boltzmann's constant, the absolute temperature, and the viscosity, while d describes the hydrodynamic diameter. From the equation, you can see that for large particles, the diffusion constant is relatively small, and thus particles will move slower. In contrast, the smaller particles have a larger diffusion constant, with rapid movement. For example, a sample with a known diameter of 100 nanometers was evaluated twice, the first with a log correlation and then with a linear correlation. Let's compare the results. You can see here that the linear correlator has a shorter range of decay time, thus suitable for very small particles with a narrow distribution. Contrast this to the log correlator, which is more commonly used for most range types, as the decay time spans 6 orders of magnitude. The top intensity distribution is log autocorrelated, while the bottom distribution is linearly correlated, and you can see that in this case, the log autocorrelator diameter and standard deviation result is closer to the standard size of 100 nanometers than the linear autocorrelator results. This data is centered with no skew. Polydispersity index describes particle variation. The closer to 0, the more uniform the particles are. As for the number and volume distributions for the top log and bottom linear autocorrelation functions, both show less skew. The analysis results are based on differential intensity. However, differential volume and number output can also be given. That's all for this installment of Ebatco Lab TV. We hope you enjoyed and will visit us again. Keep an eye out for more videos covering diverse topics from our lab. If you have any questions about either the methods or the instrument you saw here today, please don't hesitate to give us a call or shoot us an email. Our contact info can be found on our website. And as always, if you are interested in nanoscale material and device surface characterization lab services or consultation, please contact us. We'd love to hear from you.